Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks to Andrew and Peter for the invitation to be here. I thought I would talk about scalable language specification. The word scalable has been tossed around several times in the last few days. So I thought I would start by just picking apart some different notions of scalable that we might separately have in our minds, because there are lots of them. Sometimes might not have been completely clear. So one is whether we're talking about big languages or little languages. Several people have been talking about quite big languages, and slightly to my surprise, very few people have been talking about the things that semantics people usually spend their time working with, right? Which are usually these sort of more modest-sized but possibly very subtle calculi, and sometimes these semantically designed research languages. So there's an example that some colleagues and I produced a few years ago with, sort of an 80-page definition full of rules and syntax and operational semantics and type systems and that kind of thing. So we might be aiming to address any of those or all of those. Another thing that varies a lot is the subtlety of the things. You might easily have large but very boring languages. A very different thing is the requirements that the language spec puts on the meta-language that you're using, which I'm going to talk about quite a bit. An important but disgusting thing is the amount of contingent goop. Gloopy, slimy, oily stuff. It's a good word, goop. Another interesting thing is the rate of change of the language that one thinks one is trying to help the design or analysis of, which can be very high for some of these and sometimes very, very low for some of those. Something that some people here are very concerned with, but I am mostly not, is the scaling of tool performance with program size. Because mostly today, at least, I'm concerned with just defining the wretched languages in some sensible, rigorous fashion. And if you can't even do that, then the time to start thinking about tool performance has not yet started. Okay, so that's like preamble. So this is going to be a slightly strangely structured talk because it's not going to be me selling you a thing and then a big punchline at the end telling you that you should buy it. What it's going to be is me taking some snippets from 5 different research project kind of things and trying to tease out some punchlines from each of those. You may find some common themes appearing in those punchlines, you may not. So the first snippet, scalable language specification, or large-scale language specification. Well, that's a lot like large-scale specification, right? We might look at some other large-scale specification activities and look at what we had to do for those specifications and see if there's anything in common. So let me do that. This kind of activity, building a large-scale specification, you could do that at design time, or you can do that for some existing artifact. So let me talk here, both of those are good and valuable. Let me talk here about doing that for some existing artifact. So some brave colleagues and I spent quite a while, on and off, specifying the TCP network protocol and the sockets API for that protocol. So in linguistic terms, this is very, very simple. There's a programmer's level interface which just has a few calls to bind and select and read and write and that kind of thing, and a network interface on which IP packets get dropped on the wire and pulled off the wire. There's no inductive syntactic structure here whatsoever. So in that sense, this is not a language problem. but it is a specification problem. The behavior of these things is extraordinarily complicated and, unsurprisingly, terribly badly specified, even though this is an interface which most of the software and machines on the planet have to deal with. So what can we do to build a specification for that? So what we did was something that we called experimental semantics, which was not so common back then. Still not so common, despite the efforts of some of our fine colleagues in the back left corner. So what we did was to start off reverse engineering a spec from the textbooks, the code, the industrial specifications. And that spec at the end of the day turned out to be fairly big, maybe about 25,000 lines expressed in a whole 4. About 2/3 of that was comments. There were not 2 to 3 comments. That would be different. And then, so you sit there, imagine you sat there for 2 years just writing into an editor buffer these 25,000 lines, then of course you should not believe that. And therefore, the obvious thing to do is to experimentally test it. So we generated a big collection of implementation traces from actual implementations of BSD and Linux and Windows and whatnot, and check that the specs admitted those traces, and otherwise, well, maybe that's a bug in the code, or maybe it's a bug in the spec, and either way we have to fix something and go back to 1. Go to being the operative word here. So, echoing things that Sriram was saying, testing against semantics, it's great. It's the most low-cost, straightforward activity that you could possibly do, at least assuming that you're in this sort of world in the first place. And as a way of engaging with systems people, it's great because they can understand that. And especially, the thing that we were doing here was testing this correspondence between implementation and model step by step along the trace. Right? So we were very intentionally looking at the details of the state at each point insofar as we could match them up. And that's a very discriminating way of testing what's going on. And we found some bugs in the implementation that you could ask me about offline, but you would never find by normal testing. Right? They would just take absurd quantities of testing. So that's building a semantics. Somebody said, maybe several of you have said, a specification should be executable. That's a good thing. And there was, a lot of nodding going on as if we all agreed about that. So that depends, really. So let's look for a moment at the expressiveness of the language that we need to write this spec, and about what that means for executability. So it has to be a very loose specification. And it has to be a loose specification because there's a lot of variation between the implementations, different algorithms for reassembling packets and picking sequence numbers and things. And within one implementation, there's a lot of runtime non-determinism coming from timing or particular sequence numbers or operating system scheduling, all that kind of stuff. So we have to be writing a very loose spec. And it's going to be a relational thing, not a functional thing, end of the day. We also have to have a fairly complex structured state with finite maps and lists and records and all that good kind of stuff. And in order to match the implementation behavior, at the end of the day, we couldn't get rid of all of the imperative structure. There's some large chunks of C code that effectively define the behavior of a TCP endpoint. And we didn't have to model every state change, but at the end of the day, we could only chop those up into chunks of imperative stuff. So we used some relational monad structure. So this is saying you need a rather expressive specification language. And indeed, we used a pretty expressive specification language with the higher order logic of whole 4. We didn't need terribly fancy types, and so that was enough. But We're in higher order logic. Are things decidable? No. Let's think again about executability. What do we actually need? Well, what might we want? Given a spec, given any kind of a spec, we might want to do lots of very different things. So one thing is to just run the spec like an implementation, as an emulator. Just resolving that non-determinism any old how. That's useful. Another, run the spec as a daemonic emulator, using some heuristics to pick interesting paths. Yet another, to use the spec to calculate the set of all the behaviors that the spec allows for some scenario. Sometimes that's very useful, because that's what you want if you want to be able to compare that against some set of practical observations. And last, you may want it to act as a test oracle. If you've got some particular observation, you may want to decide whether the spec allows that or not. So in a deterministic world, these collapse. But here, they're all completely different. And in fact, this last one is what we needed to do. Right? We had some experimentally observed trace picked out off the wire of some test network, and a definition of the spec of some transition relation, and an initial state, and we had to decide whether there exists that path. And you can't do that in general, but in whole 4, not decidable. But for this particular spec, we could build a whole big pile of tooling that could do that in practice. Okay, another thing that you need. It's a big spec. This goes without saying to many people, but not to all of them. You have to be able to do production quality typesetting and comments and document structuring and all of that kind of stuff. So we spent quite a while building ad hoc tooling to do that kind of thing. So if I show you, this is deliberately slightly fuzzy. This is a little bit of that spec. This is one of the rules. It's quite a little bit. This is a rule dealing with a packet coming in, it's a passive open, receives a SYN packet, sends a SYNAC packet, if that means anything to you. There's a state which takes a transition to another state, and here is the side condition on that rule. You can see it's on that side mostly. And there's a lot of little comments in here. There's some careful structuring. There's use here of record update patterns so you can frame out all the stuff that you're not talking about. Echoing something Gregor was saying at the beginning. Yeah, there's a lot of attention paid to presentation. Okay, let me now shift to my next little snippet. One of the things you want from a scalable language specification is to be able to do some trustworthy meta theory. If you have a typed language, you might want to prove some type soundness results, or in some cases you might definitely not want to prove some type soundness results. So what can you do if you want to do that? Well, you've got two choices, basically. You can do pencil and paper proofs, or LaTeX proofs, or you can do mechanized proofs. And pencil and paper proofs are easy, but false. And the mechanized proofs are correct, but painful. To anyone who believes that they can do correct pencil and paper proofs or non-painful mechanized proofs, then you're a better man or woman than me. We've certainly not been able to do either of those. So a group of us back in 2005 sort of observed a situation and said, wouldn't it be nice to have a little challenge problem so we could figure out how and whether people can do mechanized proofs in the best possible style and document that style. And we took several lessons from that, but one lesson is that any language specification worth its salt has to be able to support mechanized proof of meta theory, if there is any meta theory that you care about. And that doing that sort of for real needs you to be able to produce idiomatic, or at least pretty idiomatic definitions in a good proof assistant. And there are several good proof assistants. May not matter terribly much which one, but for each particular one, it does matter what style of definition you produce, right? You know, with the right sort of inductive structure and without too much gratuitous coding and so on. Otherwise, that level of pain just becomes utterly unbearable. Right? Okay, so that's a useful thing to know. So then, let's go back to that, those different kinds of semantics that we might be aiming for that I mentioned at the start. Right? So what kind of tool support for the practicing working semanticist would actually help them get on with their job? So back to that state of the art. This is an extract from the source of one of our fine, not so fine papers, written carefully by some very careful PhD students and postdocs in the best tool available at the time. You do get that presentation. It's good. You can just about do it for small calculus, but it does get error prone even for that, I know, because of the errors that we made. But then you just get this overhead of that markup. I mean, really, it's just disgusting. And the lack of any kind of checking of any even basic sanity properties is just ridiculous. Not having any support for checking conformance between your spec and your implementations, ridiculous. And informal proof, hopeless. Option 2 is directly use one of the provers, for example, one of those 4. So you get some of that automated checking, but you have a lot of other downsides. So you more or less, you don't really get production quality presentation from any of them, in my opinion. All of them have some facilities, some more fancy than others, none that were sufficient for our purposes. You have quite a bit of syntactic noise, you do have some non-trivial encoding you have to do, but then these are maybe the most serious things. You have quite steep learning curves and long learning curves, and you have a community partition, right? There are, I don't know, there's Randy Pollock and 3 other people in the world who can really use more than one prover in a fluent way. So if you were to spend your time saying, I shall make a semantics for some important API, like, oh, why not TCP? And then you produce a whole 4 spec, and then you put that out to the community, and who can use it? The people who are already whole 4 experts and nobody else. So this is a big problem if part of your business is making specifications usable, insightful, useful specifications of the infrastructure that we depend on.
May I add a point to this?
Yeah.
Even within a group of your partition, a proof which has been done after 2 years may not be redoable.
Oh, absolutely.
The system changes.
Absolutely. So
you can read and read and read again and again.
Okay, so what can we do? So, another piece of state of the art. State of the art 2005, languages with a sort of vaguely mathematically rigorous, mainstream languages that I was vaguely familiar with a sort of rigorous definition. Blip. Sorry, sort of rigorous normative definition. Blip. And that was full of mistakes too. Languages defined by a few words and maybe an implementation. Blip. Okay, so what could we actually do about that? So here is a very straightforward kind of thing that Francesco Zappinardelli and I embarked on, and later Scott Owens and some other people joined us, was to build a very ad hoc tool to help us do the kind of semantics that we normally did. So what it does, you can write a definition of a language syntax and semantics in what we thought was a nice way, and then it compiles that to definitions in LaTeX and Coq and Hall and Isabel and now also Lem, and a bit of boilerplate in programming language. And it built some kind of a parser and pretty printer for symbolic and concrete terms of that language, so you could have examples in your papers that had actually been parsed. Okay, I'd like to draw your attention to how radical that apparently simple notion is. And there was also, so we were doing a lot of thinking at the time about how you specify binding in language definitions, which turns out to be a much more subtle problem than it ought to be. So OT included, in fact, the genesis of it was a language for specifying binding structures. So what does it look like? So I'm going to show you the smallest possible example first. I think you probably know what that is. So what do you say if you want to define that in OT? If you want to write a POPL paper in which you say, I've just had this great idea of the untyped call-by-value lambda calculus, and I want to write it down as directly as possible. You write something like that. So this is an OT source file. It's actually literally an OT source file, except that really you'd have to put these on different lines.
Can you go back for a moment?
Yeah.
Can you go forward?
Yeah.
I don't believe that. I don't believe that. Where are the words value and term and so forth on that file? You have those annotations on the right. Term, variable, lambda, app.
You get a silver staff paying attention, and we will add those in just a couple of seconds. Okay, so leaving aside those words and the font of that identifier and the typesetting of that symbol, you write that. So the blue stuff here is all, as it were, keywords, and the black stuff here is all user notation and user identifiers. So you see it doesn't know very much. Right? You've written down here, you've introduced a class of metavariables, you've written some context-free grammar using some tokens or whatever, but you didn't have to say what. You've written a grammar of values, and you've written a few inductive rules. Now, that's already enough for the system to parse it and type check it and give you some basic consistency checking as a consequence, which is fabulously, fabulously useful. Very simple, fabulously useful. And that grammar, notice, it's defined sort of the concrete syntax of terms, although we haven't actually told it enough of how to do that enough for it to know how to do that in a serious way. We haven't told it precedences or what have you. It's also defining really what it's defining is the grammar of abstract syntax that we're going to use in our semantic rules. And it's also defining some meta syntax that we're using in a few places. And there's actually quite a bit going on there already. If you just look at that rule, there's some symbolic metavariables and a few non-terminals built in some quite structured way. And that naming convention, which is standard practice in informal maths, but not usually captured in our tools, is one of the things that's letting us find errors and disambiguate things early. There's some subgrammar relationships which are declared and checked, which we use for call-by-value lambda calculus. Some user-defined syntax for judgment forms and formulae and all that kind of stuff. And that's being parsed with some kind of an extended GLR parser. So semantic rules are lovely because they're very small and not very ambiguous. So it's just fine to use more or less arbitrary context-free grammars for this kind of thing. Okay, so if you want to add in that extra bit of eye candy, then you might say, please typeset these things like that inside a math-it, for example. And you have to be able to support that kind of thing if you want people to be able to write their production quality papers with bits of semantics in with carefully tuned and designed notation. And then you might add a bunch of comments, and then you really would get exactly that thing that I showed earlier. What happened? That's also enough to let you write some ASCII syntax embedded in a LaTeX file and have it parsed and typeset properly. If you want to actually make it mean something, which I would hope everybody here would, then you need to say what binds in what. In this case, that's quite simple. That doesn't exercise much of the language. And you need to say just a tiny bit of extra data to map that into a theorem prover definition. And the tiny bit of extra data you need to say is, please, Ott, generate me a substitution function for single substitution of 1t for 1x, and call it tsubst. And then you need to say, please, Ott, this random user syntax that I've invented, I'd like that to be desugared into a use of that substitution function. And this random user syntax which I've invented, please desugar that into just a t itself. And then I'm done. And I push the button, and it tells me some error messages, and I fix those, and we repeat like that a couple of times, and each time I say, thank you, Ott, for finding my mistakes in my maths. And then it spits out definitions in your favorite theorem prover, whichever one it happens to be, which are reasonably idiomatic and readable and all that kind of stuff. So let's just reflect on the design of this thing for a second. So there's not much built in. There's not much assumption on the form of the semantics built into this thing. Right? The tool lets you define some pretty much arbitrary context-free syntax and some pretty much arbitrary inductive relations. Right? And then it's letting you, like those ways of special casing the LaTeX output, you can override its defaults. You can add clauses saying, please map this type or this production into that in this particular theorem prover, which you sometimes need to be able to do. And then, because we're really trying to support our normal working practices, there's a whole ragbag of miscellaneous features which are very handy, right? Which are not, in no sense is there a principled collection of these things. These are just things which are useful. So there are ways of defining subgrammars and grammars for sort of evaluation, well, not evaluation context, but grammars for contexts, because we're trying to be reasonably general here. Stuff to automatically generate substitutions for free variables and binding and whatnot. Support for this kind of lists, all kinds of extra ad hocery. Does it work? I tell you small facts about three examples built using this. So one was by Rok Stranica, who was a PhD student here, who went off and looked at a proposal for the Java module system after it had been sketched, but before it had been finally stamped. And he formalized that and found some flaws in it and discussed those. I think they changed the design a bit, and then he proposed a new design. Unfortunately, we were slightly behind the curve just in timing. Right? Their standardization process and the period interval in which they were prepared to revisit their choices was almost closing by the time that he had got up to speed and really engaged with it. So otherwise he might have had even more effect. People talk about modular semantics here. So Rok had 3 calculi, a core Java language, lightweight Java, and a Java extended with some kind of module system based on their original proposal, and a different one with maybe a better module system, he argued. And you can see here the overlap in the definitions, his Ott definitions of those calculi. So this was almost entirely reused in that, and that was almost entirely reused in that. And likewise, a rather rare kind of a picture to be able to show the overlap in the proof scripts of his Isabel proofs that he did about those OT definitions. So this is actual reuse within a family of closely related languages, which is doable and valuable. Let me look at the next example. So people have already mentioned Scott Owens' OCaml Lite. So I was going to print out a copy, but apparently the printers don't scale to this kind of semantics. See if this will work. Yeah, there you go. There's some semantics. And now you know what OCaml Lite is. Wasn't that good? So this is an interesting scale because it is much more than people normally address in some conference paper or other. It's quite a lot smaller than all of OCaml or F# or what have you. But it's not sort of devoid of subtlety. I mean, if you can just sort of zoom in here somewhere. There's some rules. Some of these rules are quite boring. So by chance, I've come up here with the application rule, which you can hopefully just about see at the back. Yep.
I was just going to ask, this looks huge. Is that because it also includes some details of like the delta functions, the details of arithmetic and things like that?
No, on the whole not. I think this is what it is.
Well, I don't know what it is.
So what it is the operational semantics and the type system for...
And the whole type system, okay.
Yeah. So it's that much operational semantics and that much type system, and it includes sort of all of the core ML-like stuff that you might be expecting. The language includes semantics for floats, but this is not including, these two pictures are not including the details of the float operations and all that kind of stuff. So this isn't including the standard library stuff.
People mock JavaScript.
No. This is clean and tidy. People mock JavaScript not because it's big. Sorry, I lost my chain of thought there. Oh yeah, so there are some...
You said not without subtlety.
Yeah, indeed, thank you. So some of this is quite straightforward, and some of it is a bit less so. Oh dear, that's not what we wanted. That's what we wanted. So this is the kind of rule that you might find in an ICFP paper or whatever. This is some kind of a typing rule for records. This is not very subtle, actually, but there are, there's some stuff going on. There are some tuples of derivations and a bunch of typing assumptions on fields and some other kind of stuff. So I don't want to talk about that in any detail, but I just want to show you what you would have to write in OT to express that rule, and it's that. It looks sort of the same. At least I hope it looks sort of the same. And that looking sort of the same is what lets you casually edit the collection of rules in an Emacs buffer and email them to somebody else and check them into a version control system and read the diff when somebody else changes it in a version control system and all of that kind of stuff. Right? So getting rid of the syntactic noise is more valuable than what one might have imagined. Third usage. Is this used by practicing semanticists designing new things? Well, so Stephanie Weirich and her colleagues, including Simon, although Simon is safely upstairs at the moment. I'm not sure Simon liked this part, but Stephanie made him. Used OT to design 3 generations of the Haskell core lambda calculus. Right? I'm not going to tell you anything about the Haskell core lambda calculus, but I'm going to tell you something that Stephanie said about it. So we had a little paper together in the workshop on mechanizing meta theory. Here is that little paper. Right. So Stephanie wrote this side, and we wrote that side. And Stephanie said, I plan to use OT in every new paper that I write in some form. Whew. The tool has become an important part of my design process, and I've come to rely on it. The purpose of this part of the talk is to explain why. And she goes on to explain that these facts of being able to easily manipulate the definition and toss it around with colleagues and get this basic sanity checking very quickly were just invaluable to her. Right? So as a language design tool, it does actually work. As a semantics design tool, it does actually work. Okay, so good, but, okay, there's a lot of buts. So one but, perfectly legitimate, is that you might choose, especially now, although not so much in 2005, to just work directly in Coq or Hol or Isbell. They've all got a bit better, we understand better how to use them. That's certainly doable. You still don't get all of those same things. It's more heavyweight. You don't get that production quality typesetting. You have to do your own encodings of some things. Thing that OT certainly doesn't do, so it generates this parser for symbolic terms, but it doesn't generate a production quality parser or pretty printer that you can use in a standalone language implementation. And it would be great if we could figure out how to tell it to do that, and surely the user will have to add a bit more information to make that possible. The type system, well, I say type system, so this language of context-free grammars with subrules, that's a type system. There's no parametricity in it, and that turns out to be surprisingly annoying, because not only do you want to write stuff in your user-defined abstract syntax of the language you're defining, sometimes you mostly just write that stuff. So for OCaml-Lite, you mostly just write that stuff and it's fine. But sometimes you want to write a whole pile of auxiliary definitions directly in higher order logic or in some kind of functional language. And for that, you really need just a bit more parametricity, otherwise it becomes too annoying. And OT doesn't at all produce executable semantics. Well, clearly you don't have to do that, because I've just described 3 very useful cases in which we didn't do that at all, and we still got some benefit, but it would be nice to do that. So now let me switch to my 4th little snippet. So this was motivated by our experience doing work on sort of standard programming language semantics. And after that, several of us started working on other kinds of semantics, so specifically machine semantics and on the concurrency semantics that you find in shared memory programming languages. And what we found then was that we were not, on the whole, working with an elaborate inductive syntax. The particular semantics that we were building didn't involve that kind of syntax at all. Instead, what we were writing was sort of standard, higher order logic, functional programming and inductive relation definition. And we wanted a similarly lightweight way of doing that. So we proceeded to invent, Scott Owens was, again, one of the main initial guys in this, another meta-language, Lem. So OT is good for user-defined context-free syntax and inductive relations. Lem does not support user-defined syntax in any way to speak of, and then lets you have a rich family of types and functions and inductive relations. And in fact, you can tell OT to generate Lem definitions, so the two are somewhat integrated, although not as tightly as they might be. So it's the same kind of story, right? So you write some definitions, with useful stuff. The definition language, it's sort of the intersection of the definition languages of those provers. And then it's giving you lightweight stuff. It's giving you type checking, decent typesetting, output that, insofar as possible, preserves comments and white space and so on. So you're getting idiomatic, readable definitions in those targets. Right? And some camel boilerplate, and in fact, now someone's working on the inductive relation execution too. So, let me give you two examples of usage of that. So this is Sarkar et al.'s work on building a semantics for the concurrency behavior of power and ARM multiprocessors. So this is, again, this kind of experimental semantics deal. Right? We're not formalizing an existing industrial spec, because the existing industrial specs are nonsense. Right? And indeed, the architects don't always know what they intend. They know what they build pretty well, but they don't always know what they intend the architectural envelope that they specify to be. So what we do here, we do another of these big loops. We generate tests fairly seriously. We build test harnesses. We run tests on actual silicon, and also inside the processor vendors, they run them on pre-silicon. And this has found various more or less serious bugs in the processors or the pre-silicon designs. And then we have a model, which is a moderately large-scale spec, not huge, written in Lem. And we, executable. Do we need to be executable? Here, by golly, yes, we need to be executable, because we need to compare what the model says with what the actual hardware says for all of those umpteen thousand tests, and we need to do that automatically. So here, we need to be able to take the model, take a small test program, and calculate the set of all allowable outcomes. And we also need to have a good presentation and have some friendly architect accessible English version of the model, so we can argue with them about it, because they're not going to argue with us about the details of the higher order logic rules. We need to talk with them, and then we repeat. And then every so often, we need to try to use these models for doing some software or hardware verification, and then repeat.
So, question? So the hardware guys provide you tests, and you write models in mathematics and in English?
No. We provide them tests.
So what do? They just say yes or no?
So, did you say the hardware guys or the hardware?
Hardware.
The hardware says 3 or 4.
Right.
The hardware guys have a much more interesting dialogue in which they say things like, okay, I'm not actually going to tell you this, but our microarchitecture might be a bit like such and such. Or they may say, as far as I can tell, your model is consistent with the external behavior of my hardware and with the architectural intention of my hardware, but it would be confusing to tell my hardware partners your model because the internal structure is different. That's a nice thing when they say that. Or they say, yeah, I can get my head around that. Or they say, well, that's a good question. I don't know. I'll go and ask my other designer friends and see what we think we aim to build. They say all kinds of interesting things. But without, if we were just doing black box testing, there would be no hope. We don't have enough information about the internal structure. It's got too much internal state to infer that just by experiment in a reasonable amount of time. We depend on them being somewhat informative.
So how do you write that red line, number 3? How do you do that? Just by reading the spec and all that?
No. But by this whole iteration of understanding how the stuff is actually working, understanding what kind of properties they mean to provide, understanding what you need to know in order to implement higher level languages above these things. A lengthy iteration. making wrong models. So we made, I don't know how many wrong models on the path to this.
Version controls. Only versions.
We've used multiple different version control systems. Does that help? I mean, yeah, that's a measure of. Okay, so so executable. Executable, sure. Okay, so this is the Lem model, which I've not shown you any of, but I happily can. It's compiled by Lem to OCaml code, compiled by OCaml to OCaml bytecode, compiled by OCaml.js to JavaScript, and running in the browser. So it's a highly, highly trustworthy tool chain. So I shall pick from our library of tests a test. Let me pick that one, that's always a good test. So there's a little test. This is a typical kind of a test. It's a fairly small one. There's a power assembly program. You've got a little assembly program for this thread and a little assembly program for that thread. And then I might run that exhaustively, or I might run it interactively. And this, although I'm not going to explain the detail, is the state of the abstract machine of that model. And these green things are the system having computed that the precondition for those transitions is true in that state. So then I could say, why don't I take that transition and the state changes, or I could take that transition. Maybe this will be more interesting. I could take that transition, and you can see I can just sort of interactively walk through that and explore what the model means. Right? And the model is a bit subtle, so being able to do that is invaluable. So in fact, we need to do this interactively and exhaustively in order to get anywhere. Okay, another usage. So Mark Batty, who's a PhD student here, a bold and brave PhD student, embarked on trying to make sense of the C and C++ concurrency model. When he started doing this, the concurrency subgroup of the C++ Standards Committee had been agonizing about the concurrency model for several years, maybe 5. And they produced some kind of a prose draft proposal in the way of standard committees, you know, the kind of thing. So Mark came along and said, I shall read this, or at least read, section 1.10 and chapters 29 and 30, which were the only ones that mattered. And he proceeded to try to formalize this with, several of other people involved too, and find some medium serious but not major conceptual mistakes and propose fixes to those, and traipse along to the Standards Committee and explain those fixes. And indeed, explaining those fixes with concrete examples that we had run in some mechanized tool, so we had some confidence in them, was a fine way of interacting with the Standards Committee, whereas dumping 2,000 lines of higher order logic on their heads would not have worked. I know that it wouldn't have worked because even though, so these are very smart people who do know what they're doing in many, many ways, and they know a lot more about the languages and about compilers than we do, but if you accidentally show them, some kind of an upside down A, then they will accuse you of perpetrating Greek letters, and the whole, I kid you not, the whole tone in the room will go down and cold, and it won't work so well. So one has to be careful to sort of go to them rather than vice versa. Right? So here we have a model, but it's not an operational model. It's what people call an axiomatic memory model, not to be confused with an axiomatic semantics in the conventional sense. But here you might take some example program. I think my internet might have gone away, so maybe this won't work. Maybe I'll pretend. So you take some example program, and then you run it. No, it worked. And it calculates the set of all model allowable executions. There are 8 of them here. Each single execution looks a bit like this. It's a graph with a bunch of read and write events and various relations. And then you can step through them and see which ones are consistent or not according to some predicate. And then you might say, oh, the coherent memory use axiom is violated for this example. And then you might go away and read where's it gone? I've lost it. Read the coherent memory use axiom and see if it actually says what you meant, and so on, and then go back and iterate. So it's not always so that's again sort of automatic, right? We're executing the model more or less as it is, but you can't always expect to do that, right? And sometimes much more cleverness is involved. So Francesco Zappinardelli has just had a paper at PLDI last week in which he tests actual C compilers to see if they do optimizations allowable by this model. And in order to do that, he had to do all manner of sophisticated, first just instrumentation of the compilers, following some clever scheme, but also proving facts, laboriously and by hand, about what kind of optimization the model allows. So that's not going to be automatic. Time is ticking along, so let me go very quickly to my fifth little case. Scalable language specification. What about scalable language specification for machine languages? x86, there's a good programming language. It is a good programming language because it's, on the whole, very, very stable. People are going to keep on caring about x86 for a long time, unfortunately. Or ARM, or Power, or any of those. So there's a lot of things that are similar to what's gone before, right? They're quite large. There's a lot of contingent goop, really a lot. If you're going to do this at all, you'd want to make it available for multiple usages by multiple users in multiple communities. Otherwise, it's just not worth the effort. You have to be able to test semantics against implementations. And again, it's a very loose spec, so I can't really overemphasize the importance of this enough. If you're in deterministic land, then you can just have specs which are pure functional programs written in almost anything. It doesn't matter, right? And you can do some of this testing stuff. But when they start to be more non-deterministic in any of the many different ways, life is more fun. But it's different from normal languages in that there's a big syntax, but it's very flat. No inductive structure to speak of. You can, I think, get away with a first-order description of the behavior of the individual instructions, although then you have to glue that onto the memory model, which is a whole other story. It's sufficiently big that it's worth having domain-specific language support for doing just this, although there are not so many processors that you have to sell that to the whole world. Right? There are not going to be very many programmers in this metalanguage, hopefully. So a thing that we're doing at the moment is, in fact, we were doing some of it in a small way in the very lunch break here, is defining a domain-specific language, actually defined in OT, because that would be our preferred tool for defining languages like that, and compiling that via Lem so you can glue on these concurrency models into multiple targets. Okay, so here were 5 little snippets. Right? Well, really 4 different, I've told you about 4 different meta-languages. And they're all quite general purpose. Right? So none of these, except possibly the last one, have any built-in commitment to, are you doing a reduction semantics or a big step operational semantics or a rewrite system or anything like that, right? They're quite general purpose things, but their expressiveness is sort of tuned for the application. So here, we seem to really need all of whole 4. Here, in the common case, for programming language definitions, a bunch of inductive relations is just fine. Here, we really needed a little bit more polymorphism, but not terribly much. Right? And in each of these, we're putting in a lot of work into supporting the kinds of activity that we do as supposedly working semanticists, right? And focusing on expressing the stuff as cleanly as possible, but paying a lot of attention to all these other thingies. Okay, so before I stop, let me see, what do I want to say about this? Modularity. So modularity is an interesting word here. Right? It sort of suggests an analogy with modular programming. And we know, you wouldn't want to write programs as a big monolithic pile of code. That would be bad, very old-fashioned. But let's just think for a second about the scale that we're talking. So I've said, oh, here's some enormously big, scary specs. And so have some of you in some of the earlier talks. And what's an enormously big, scary spec? So that TCP model, that was 9,000 non-comment lines of whole 4. And that was enough to consume several people's attention for several man-years. Right? That power operational memory model, that's like 3,000 or 4,000 lines of Lem code. Okay? So by the standards of the semantics that you might find in an ACM 9.2 column paper, that's quite big. But by the standards of the pieces of code which we're used to chucking around every day, that's quite tiny. And that's on a scale where it's not that painful, at least if you've got some tool support to identify the stupid errors, which we do. It's not that painful to go through and apply, search and replace operations and cut and paste and generally hack it around. So for defining these languages when working with a family of related languages, as Rock did in LJ, then it's absolutely identifying the modularity which is there is very valuable. But in the grand scheme of things, it's not the same problem as software engineering. It is a different thing. We would love to have, so if we could do, if there was a realistic prospect of doing modular type soundness proofs in a way that would let me reuse some substantial chunk from one language to another, that would be lovely. But then I look at the OCaml type system and the Java type system and the Lem type system and pretty much any other substantial type system that I can think of, and I don't see that much commonality. So I think we need some other, thing which is not the software engineering notion, because we don't, on the whole, want to compose these things from and then only do proof or apply our tools to the results of those tools applied to the components. Right? We have more freedom than that because the scale is not that enormous. So there's a lot of places where I think one can see that one can use a bit of semantic engineering, rephrasing one's definitions in a more convenient style to pull out the modularity that you may have within some particular family. So I think I have gone on for long enough, so let me end by just putting that up there from 49 years ago and ask you to contemplate how far we've got since then, if anywhere. Thank you.
Thank you very much.